You know how sometimes numbers seem to follow a hidden set of rules? It's almost like a secret code, just waiting for someone to come along and crack it. Well, today, that's exactly what we're going to do. We're going to become decoders. So let's kick things off with our main mystery. Look at this sequence: 2, 4, 6, 8. You can probably guess the next number is 10. That's easy. But what about the 103rd number in that line? I mean, writing them all out would take forever. There's got to be a better way, right? And you'd be right. The good news is there is a much, much better way. It's kind of like learning the grammar of this secret number language. Once you get the rules down, you can skip right to the end of the story without having to read every single page. All right, so before we can start decoding, let's get our terms straight. What are we actually looking at here? What do the pros call these things? It's called a number pattern. Simple enough. And each number in the line is called a term. So you have the first term, the second term, and so on. The really important thing is that these numbers aren't random at all. They're all connected by a specific rule. And our job is to find that rule. Now, these patterns come in two basic flavors. On one hand, you've got a finite pattern. It has a clear beginning and a clear end, like the odd numbers from 3 to 11. That's it. It's done. On the other hand, you have an infinite pattern, and you guessed it, it just keeps on going forever. That's what those 3 little dots at the end mean. Our mystery with the even numbers, that's an infinite one. Okay, so we know what they're called, but how do we actually find the rule? How do we find that key that unlocks the whole pattern without all the guesswork? This is really the big question, isn't it? We're on the hunt for a shortcut, a tool that lets us just leapfrog over all the numbers in between and land directly on the 103rd term, or the 500th, or heck, any term we want. Well, what if I told you that tool actually exists? Imagine having a single master key that can unlock any number in the pattern, just by knowing its position in line. Sounds pretty cool, right? Let's build one. Let's go back to our even numbers and really break them down. The first term is 2, which is just 2 times 1. The second term is 4. That's 2 times 2. The third is 6, which is 2 times 3. Are you starting to see it? The value of any term is just 2 multiplied by its position in the sequence. This rule actually has a name. It's called the general term, and this is our master key. In algebra, we use the letter n to stand in for any position in the sequence. So for our even numbers, the general term, our master key, is just 2 times n, which we write as 2n.
So now we can finally solve our big mystery. We wanted the 103rd term. Using our master key, 2n, we just swap out n for 103. So 2 times 103 is 206. And just like that, mystery solved. No tedious counting needed.
This master key idea is incredibly powerful, and it doesn't just work for even numbers. Let's use it to unlock a few of the most famous patterns in all of mathematics. Let's take the odd numbers: 1, 3, 5. Now think about it. Every odd number is just 1 less than an even number, right? So if the key for even numbers is 2n, it makes perfect sense that the key for odd numbers is just 2n minus 1. It's so elegant how these rules are all connected. All right, let's try another famous pattern, the square numbers: 1, 4, 9, 16, 25. They're called that because you can literally arrange them into perfect squares. But what's the algebraic rule? What's the master key? The secret is hiding right there in the name. The first term is just 1 times 1, or 1 squared. The second is 2 times 2, or 2 squared. The third is 3 times 3, so the nth term is just going to be n times n, or n squared. Boom! Another code cracked. Okay, how about one more? These are called triangular numbers because, well, you can arrange them into triangles. The sequence goes 1, 3, 6, 10. This one might not seem as obvious, but I promise, the logic behind it is just as cool. Here's how they're built. The second term, 3, is just 1 plus 2. The third term, 6, is 1 plus 2 plus 3. The fourth is 1 plus 2 plus 3 plus 4. You're always just adding up the position numbers. The master key for this looks a bit fancier. It's n times n plus 1, all divided by 2. But it's a fantastic shortcut and just as powerful as the others. So we've unlocked the codes for some of the most famous patterns in math. But you might be asking yourself, okay, but why does this actually matter? Well, let's see how this code-breaking skill applies outside of a textbook. Take a look at this. It's a real-world scenario. A population starts at 2 million and grows by 2 million every 25 years. I don't know about you, but that sounds an awful lot like a number pattern, which means we can use our new skills to look into the future. Let's predict the population in 200 years. The pattern happens in 25-year chunks. So 200 years divided by 25 gives us 8 terms. Our n is 8. The rule for the increase is $2n million. So 2 times 8 gives us a total increase of 16 million. Add that to the starting 2 million people, and we predict a future population of 18 million. We just used a simple number pattern to do some forecasting. So what's the big takeaway from all this? It's that these patterns aren't just abstract puzzles. They are powerful tools for understanding the world and even making predictions about it. And here it is, your brand new pattern cracking toolkit. You now have the master keys for some of the most fundamental number patterns out there. Think of these as your building blocks for seeing hidden structures everywhere. And that's the real power of what we learned today. It could be population growth, it could be the financial markets, it could even be the petals on a flower. Identifying that underlying pattern is always the first step. Once you find the rule, you gain the ability to predict what might come next. So I'll leave you with one last puzzle to chew on. A pattern starts with 1, 2, 4. What do you think comes next? Is it 8 because you're doubling each time? Or could it be something else entirely? As it turns out, sometimes